Episode 37, titled Cloud Interconnects, Direct Connect, ExpressRoute, SDCI Selection Logic, we treat private cloud links as a predictable connectivity and security improvement because the biggest change is moving key traffic off the public internet and onto a controlled path. The exam often frames this as a connectivity upgrade, but the deeper point is that private interconnects change risk and performance characteristics in ways that matter for migration, compliance, and steady-state operations. When workloads move between a data center and a cloud region, the network path becomes part of the application, and unstable latency or uncontrolled exposure can become the bottleneck. Private interconnects exist to reduce that uncertainty, providing more stable behavior and clearer control of routing and monitoring. They also shift governance because you now have circuits, routing policies, and redundancy plans that must be designed deliberately rather than assumed. The goal here is to build selection logic that tells you when a dedicated interconnect is justified, when a software-based Internet virtual private network is enough, and how to avoid the most common high availability and routing traps. Before we continue, a quick note. This audio course is a companion to the CloudNetX books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyberauthor.me in the Bare Metal Study Guide series. Dedicated interconnects are attractive because they provide stable latency and reduced internet exposure, which improves both performance predictability and security posture for many hybrid workloads. Stable latency matters when applications are sensitive to round trips, when replication traffic is steady, or when users notice jitter and timeouts during busy periods. Reduced internet exposure matters because traffic traverses fewer uncontrolled networks, lowering the risk of interception and reducing dependency on variable internet routing paths. This does not remove the need for encryption and identity controls, but it does reduce the number of places where traffic can be observed or interfered with, and it often simplifies governance because the path is more deterministic. Dedicated links also tend to support higher steady throughput more reliably than shared internet paths, which matters for migration, backups, and data-intensive hybrid patterns. In exam scenarios, cues like steady high bandwidth, consistent throughput required, and compliance requires private connectivity often indicate a dedicated interconnect is the best fit. The key is that the benefit is predictability and control, not just speed. The common model is provider edge to cloud edge with private circuits, meaning your enterprise reaches a provider presence and then uses a private circuit into the cloud provider's edge rather than sending traffic over the public internet. The provider edge might be in a co-location facility or a carrier hotel where you connect your equipment or your provider to the cloud on-ramp. The cloud edge then terminates the private connection into the cloud region, allowing you to route private address space and treat the connection as an extension of your wide area network. This model reduces reliance on public internet routing and often supports consistent quality because the path is engineered and monitored in a more controlled way. It also introduces planning considerations such as where the on-ramp is located, how far it is from your sites, and whether the path is diverse enough to meet availability goals. In exam reasoning, when a scenario describes a private circuit into cloud, this is typically the implied model, even if the prompt uses generic terms like private interconnect. The practical takeaway is that private interconnects are usually built through a provider-to-cloud edge relationship, not by a magical direct cable from your building into the cloud region. Software-defined cloud interconnect, often shortened to SDCI, is a provider-managed private link option that can be faster to deploy because it leverages provider infrastructure and automation rather than requiring you to build and manage all interconnect components directly. SDCI often provides a menu of cloud connectivity options delivered as a managed service, allowing enterprises to provision private connectivity more quickly than negotiating and installing dedicated circuits end-to-end. The value is speed and reduced operational burden because the provider handles parts of the transport, on-ramp, and sometimes monitoring and service-level responsibilities. The trade-off is that you are relying more on a third party's implementation choices and operational processes, which can affect how much control you have over routing policy, visibility, and troubleshooting. In exam scenarios, SDCI tends to fit when the prompt emphasizes faster deployment, limited internal networking staff, and a need for private connectivity without lengthy build cycles. The best answer acknowledges that SDC can deliver private connectivity benefits while reducing deployment friction, but it still requires good routing and redundancy design. The key is that SDCI is a managed path to the same goal, not a fundamentally different goal. Dedicated links are most justified for steady, high traffic and compliance needs because those are the conditions where predictability and controlled exposure deliver measurable value. Steady high traffic includes continuous replication, large migration waves, frequent backups, and high-volume application traffic between environments. These patterns can overwhelm or destabilize internet-based paths, especially when the organization needs consistent throughput rather than bursty performance. Compliance needs often include requirements for private connectivity, evidence of controlled access paths, and reduced dependency on public transport for sensitive data flows, though encryption and identity controls remain essential. Dedicated links also make sense when latency sensitivity is high and when the business impact of connectivity variability is severe because predictable behavior reduces outages and user complaints. In exam scenarios, when you see high throughput required, sustained data transfer, or regulated traffic, dedicated interconnect choices are often favored. The decision is not purely technical. It is economic and governance-based. If variability costs the business more than the circuit, predictability is worth paying for. Internet virtual private networks remain a strong option for smaller or temporary connectivity requirements because they are simpler to deploy and can be sufficient when traffic volumes are modest and when the organization can tolerate some variability. Internet virtual private networks are often used for early migration phases, development and test connectivity, temporary projects, or small sites where a dedicated circuit would be overkill. They can be provisioned quickly and can provide encrypted connectivity over the public internet, which can satisfy confidentiality needs when combined with strong identity and access controls. The trade-off is that performance and latency can vary, and the path depends on internet routing, which can change without notice and can be affected by congestion. In exam logic, when the prompt emphasizes temporary, small, pilot, or cost-sensitive, a well-designed internet virtual private network can be the best answer because it meets needs without long lead times. The best answer usually acknowledges that the choice is about right-sizing to the requirement rather than about maximizing engineering. Internet virtual private networks are often the right tool when predictability is not the primary constraint. Redundancy is where many designs succeed or fail, and dual circuits and diverse paths reduce single provider failure by ensuring that one cut, one device outage, or one provider issue does not isolate the cloud connection. A single private circuit can be very reliable, but it is still a single path, and failures happen at multiple layers, including physical cuts, provider maintenance, on-ramp facility issues, and cloud edge incidents. Dual circuits provide path diversity, and the best designs also aim for diversity in physical routes, termination points, and sometimes providers, because diversity is what reduces correlated failure. Redundancy also includes routing design so that failover is predictable and does not create asymmetric paths that break stateful inspection or confuse monitoring. In exam scenarios, if the prompt includes high availability requirements, the best answer usually includes dual links and explicitly mentions diverse paths rather than assuming one high-quality circuit equals availability. The key is that high availability is a property of the whole design, not of a single circuit type. Private interconnects improve predictability, but redundancy is what improves survivability. Consider a scenario migrating data center workloads needing consistent throughput, such as a large data migration and ongoing replication between on-premises and cloud during a transition period. In this case, steady throughput and predictable performance matter because migration schedules and replication lag are sensitive to capacity and variability. An Internet virtual private network might work for small migrations, but for sustained high-volume movement, it can become unpredictable and can consume Internet bandwidth that is needed for other services. A dedicated interconnect provides a more stable path for large transfers, reducing the chance that congestion or routing changes derail the migration window. It also supports a smoother hybrid phase because ongoing replication and cross-environment calls remain predictable while systems are split across environments. In exam reasoning, this scenario often favors a dedicated interconnect, possibly combined with an Internet virtual private network as backup, because the outcome is consistent throughput under load. The best answer also tends to include planning for redundancy and routing policy to ensure the migration path is resilient. The key is that migration is a performance and reliability event as much as it is a data event, and interconnect choice shapes that reality. A major pitfall is assuming one circuit equals high availability, because a single link, no matter how premium, still has a single failure domain and a single set of dependencies. A circuit can fail due to a physical cut, provider equipment failure, a maintenance event, an on-ramp facility issue, or a routing misconfiguration, and when it fails, the organization can be completely disconnected from critical cloud resources if no alternate path exists. Even if the link is restored quickly, the outage can violate service-level requirements and disrupt production workloads, especially when cloud resources are now part of core operations. The exam often tests this by presenting a private link option and asking for the best way to make it resilient, where the correct answer involves dual circuits and diverse paths rather than just buying a bigger single link. High availability also requires testing, because untested failover can fail in practice due to routing policy, firewall state, or misconfigured prefixes. The lesson is that availability is designed through redundancy, diversity, and validation, not purchased through a single circuit. A correct answer treats one circuit as a good start, not as a complete solution. Another pitfall is misaligned routing policy causing asymmetric traffic across links, which can break stateful inspection and confuse monitoring even when both circuits are healthy. If outbound traffic prefers one path while inbound traffic arrives on another, stateful security devices may not see both directions of a flow, causing intermittent failures that look like application bugs. Asymmetry can also complicate performance analysis because telemetry is split across paths and path characteristics differ, making it hard to understand whether latency problems are due to one circuit or due to routing decisions. In BGP-driven hybrid designs, Preference rules must be planned deliberately so that primary and backup behavior is consistent and so that failover does not create unexpected route flaps. This is especially important when using two circuits to the same cloud region because you want predictable behavior during both healthy and degraded states. In exam scenarios, when the prompt mentions unexpected path behavior or traffic splitting, routing policy misalignment is a likely underlying cause. The best answer typically includes planning BGP policy and monitoring so that path selection is intentional and observable. There are quick wins that reduce risk, such as planning border gateway protocol policies, prefixes, and monitoring early, because routing is the control plane that determines whether your interconnect behaves as intended. Planning prefixes means deciding which address ranges will be advertised over which connections, ensuring overlap is avoided, and ensuring that only intended networks are reachable across the private link. Planning policy means deciding which link is primary, how failover occurs, and how route filtering prevents accidental leaks or unintended transit behavior. Monitoring means tracking session health, route counts, reachability tests, and latency trends so you can detect degradation before users do. Early planning matters because retrofitting routing policy after circuits are live often leads to production changes under pressure, which increases risk. In exam reasoning, answers that include policy planning and monitoring are often favored because they acknowledge that private connectivity is not self-managing. The link is only as useful as the routing policy that controls it. The practical message is that interconnect design is as much about control plane intent as it is about physical circuits. A memory anchor that captures the selection logic is private link, predictable, redundant, policy-controlled routing, because those are the defining properties of a mature cloud interconnect design. Private link reflects the goal of moving critical traffic off the public internet and onto a controlled path. Predictable reflects the performance and exposure benefits, especially for steady, high-traffic and compliance-driven workloads. Redundant reflects the need for dual circuits and diverse paths because one link is not high availability by itself. Policy-controlled routing reflects that border gateway protocol design. Filtering and preference rules determine which path is used and how failover behaves. This anchor helps you answer exam questions because it maps directly to the reasons you choose a dedicated interconnect and the safeguards you must include. It also prevents the common mistake of treating the interconnect as a simple plug-in-and-forget link. When you can recite this anchor, you can justify both the selection and the required design discipline. To end the core, select an interconnect type based on constraints, because the exam often presents mixed requirements that force you to choose between speed of deployment, performance, and governance. If the constraint is sustained high throughput, stable latency, and compliance expectations, a dedicated interconnect is usually the best fit because predictability and reduced internet exposure are dominant. If the constraint is rapid deployment with limited internal network expertise, a provider-managed option such as SDCI can be a strong fit because it delivers private connectivity benefits with less provisioning friction, assuming routing and monitoring are still designed carefully. If the constraint is small traffic volume, temporary need, or early pilot connectivity, an Internet virtual private network can be the best fit because it is quick, cost-effective, and sufficient when variability is acceptable. In all cases, you consider redundancy because the business outcome often depends on continuity, and you consider routing policy because it determines whether the chosen link behaves as intended. The best exam answer is the one that explicitly matches the primary constraint while acknowledging the required safeguards. When you can state the selection in one sentence tied to constraints, you are applying the decision logic the exam rewards. In the conclusion of episode 37, titled Cloud Interconnects, Direct Connect, ExpressRoute, SDCI Selection Logic, private cloud links are chosen to improve predictability and reduce internet exposure, especially for steady, high-traffic, and compliance-driven workloads. The common model is provider edge to cloud edge private circuits, and SDCI offers a provider-managed path that can accelerate deployment while still delivering private connectivity benefits. Internet virtual private networks remain a solid choice for smaller or temporary needs where variability is acceptable and cost and speed matter. High availability requires dual circuits and diverse paths because one circuit is not enough, and routing policy must be planned to avoid asymmetric behavior and unexpected path selection. You gain quick wins by defining border gateway protocol policy, prefix advertisements, and monitoring early so the interconnect behaves predictably and is observable during failures. You keep the anchor private link, predictable, redundant, policy-controlled routing as your guiding lens for both design and exam answers. Assign yourself one redundancy plan rehearsal by describing, aloud, how you would build two diverse paths to the cloud, how routing would prefer one and fail to the other, and what you would monitor to confirm the design is healthy, because that rehearsal is the practical skill the exam is testing. Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.